Okay, so we stop in the most popular 802 standards today. Um, so the most popular are actually 802.3, essentially Ethernet, and 802.11 or Wi-Fi. These standards have evolved over time and have changed names as freestanding amendments. 802.11g are ultimately incorporated in revised standards. Other than specific type of LAN networks defined by 802.3, 802.11, 802.16 standards, there are some related standards that apply across all of the IEEE standard LAN technologies. Common to all of these is the 802.2 standard that defines the logical link control frame header, common among many of the 802 networks frame formats. So the frame header, which defines the LLC or logical link layer, are common among all of the standards. In IEEE terminology, LLC and MAC are sublayers of the link layer, where the LLC, mostly frame format, is generally common to each type of network, and the MAC layer may be somewhat different. So the common is the LLC, while the MAC may be somewhat different. While the original Ethernet made use of CSMA/CD, for example, WLANs or the Wi-Fi often make use of CSMA/CA, which is collision avoidance. So instead of CSMA/CD, it actually uses collision and avoidance. Unfortunately, the combination of 802.2 and 802.3 define a different frame format from Ethernet 2 until 802.3x. So again, unfortunately, the combination of 802.2 and 802.3 define a different frame format from Ethernet 2 until 802.3x finally rectify the situation. It has been incorporated into 802.3-2008. In the TCP or IP world, the encapsulation of IP datagrams is defined in RFC 0894 and RFC 2464 for Ethernet networks, although the older LLC or SNAP encapsulation remains published as RFC 1042. While this is no longer much of an issue, it was once a source of concern, and similar issues occasionally arise. The frame format has remained essentially the same until fairly recently. To get an understanding of the details of the format and how it has evolved, we now turn our focus to these details. So the format for this has been the same for LAN and MAN standards, but there are some nuance in details which we're gonna discuss. The Ethernet format, all Ethernet 802.3 frames are based on a common format. Since its original specification, the frame format has evolved to support additional functions. Figure 3.3 shows the current layout of an Ethernet frame and how it relates to a relatively new term introduced by IEEE. The IEEE packet, a somewhat unfortunate term given its uses in other standards. So we don't want the packet because the frame shall be used in Ethernet, because packet has been used, but it has been used by IEEE. So the Ethernet IEEE 802.3 frame format contains source and destination addresses, an overload length or type field, a field for data, a field for data, and a frame check sequence, so FCS. Addition to the basic frame format, provide for a tag containing a VLAN ID and a priority information, which is the 802.1/p/q. So these are where the priority, which we're gonna discuss in the next video. So that's where the costs determine how this data packet is prioritized among the networks. And more recently, for an extensible number of tags, the preamble and SFD are used for synchronizing receivers. This preamble is the first one that the Ethernet received from the other side to synchronize receivers. When half duplex operation is used with Ethernet running at 100 millibytes per second or more, additional bits may be appended to short frames as a carrier extension to ensure that the collision detection circuitry operates properly. So again, when half duplex operation is used with Ethernet running at 100 millibytes per second or more, additional bits may be appended to short frames as a carrier extension to ensure that the collision detection circuitry operates properly. So we're gonna discuss the carrier extension, but basically for Ethernet running at 100 millibytes per second or more, additional bits may be appended to short frames as a carrier extension to ensure that collision detection circuitry operates properly. The Ethernet frame begins with the preamble area used by the receiving interface circuitry or the receiver or Ethernet on the other side to determine when a frame is arriving and to determine the amount of time between encoded bits, called clock recovery. So these are used to determine when a frame is arriving to the other end and the amount of time between encoded bits. Because Ethernet is asynchronous LAN, so you can send data asynchronously or at the same time or concurrently. Precisely synchronized clocks are not maintained in each Ethernet interface card. The space between encoded bits may differ somewhat from one interface card to the next. Because the Ethernet is a synchronous LAN, precisely synchronized clocks are not maintained in each Ethernet interface card. The space between encoded bits may differ somewhat from one interface card to the next. The preamble is recognizable pattern 0xAA typically, so that's how it starts, which the receiver can use to recover the clock by the time the start frame delimiter SFD is found. So the preamble is this pattern which the other receiver or Ethernet will receive to recover the clock by the by the time the start frame delimiter is found. By the time this SFD is found. So the SFD has fixed value 0xAB. Note the original Ethernet encoded bits using a Manchester phase encoding MPE with two voltage levels. With MPE, bits are encoded as voltage transitions rather than absolute values. For example, the bit 0 is encoded as transition from negative 0.85 to positive 85 volts. So that's actually how the Ethernet read this encoded bits. using if it started from negative 85 to positive 85, a 1 bit is encoded. And for positive 85 to negative 85 transition, it indicates that for example, the bit 0 is encoded as transition from negative 85 to positive, and a 1 bit is encoded if of positive 85 to negative. Now 0 baud indicates that the shared wire is idle. It means that no packet is being sent between the two Ethernet. So the 10 millibytes Ethernet specification required network hardware to use an oscillator running at 20 MHz. So it needs that oscillator at the first invention of this Ethernet, because MPE requires 2 clock cycles per bit. The bytes 0xAA or 10101010 in binary present in the Ethernet preamble would be a square wave between positive 85 and negative 85 with a frequency of 10 MHz. So because we have this positive and negative with a frequency of 10 MHz, we need a 20 MHz. So Manchester encoding was replaced with different encodings in other Ethernet standard to improve efficiency. The basic frame format includes 48-bit, 6-byte destination, and source address fields. So these are the basic frame format. These are the DST and SRC. The addresses are sometimes known by other names such as MAC address, link layer address, 802 address, hardware address, or physical address. So when they say a MAC layer address, they usually talk about this destination or source address. The destination address in an Ethernet frame is also allowed to address more than one station, called broadcast or multicast. So the DST in this Ethernet is also allowed to address more than one station. So you can put multiple address in this layer. That's what you call broadcast or multicast. See chapter 9. The broadcast capabilities used by ARP protocol and multicast capabilities used by ICP CMP v6 protocol to convert between network layer and link layer address. So if you're wondering how ICMP were able to detect the error, it uses this address or destination address for multiple address among the network. Following the source address is a type field that double as a length field. Ordinarily, it identifies the type of data that follows the header. So this usually identifies the type of data, which is this link that follows that header frame. So remember that the frame started with preamble and then SSD, and then we got the DST and SRC. So that usually defines this length or type defines the data that follows that. So the value 0x8100 indicates a Q-tag frame. Popular values used with TCP or IP networks include IPv4 0x800. So this length or type could have 0x800 or 0x8600 for IPv6 and ARP 0x0806. The value 0x800 indicates a Q-tag frame. So that's the length type, okay? So for TCP IP networks that are usually encoded in that Ethernet part or slice. So now the value of 0x8100 indicates a Q-tag frame. So if you have 0x800 here, it means it's a Q-tag frame, one that carry a virtual LAN or VLAN ID according to 802.1q standard. So we have, if we have QTAG frame, it means a virtual LAN. It's a more advanced type of LAN that not just connect Ethernet via switch, but actually only connect stations that is in the same LAN. So the size of the basic Ethernet frame is 1518 bytes, but the more recent standard extended the size to 2000 bytes. So this Ethernet frame, the whole of this is usually 1518 before, including this, the actual IP datagram. So this is how you encapsulate the IP datagram in details, but to understand this better and how it became 2000 bytes, we need to understand this structure. Ethernet frame is equals to header plus payload plus trailer. So kind of like all of the structure of data, you have a header, the actual IP or that packet, and the trailer. The structure being described in your code is destination MAC, which is 6 bytes, source MAC 6 byte, type or length field 2 bytes. So that's the destination address. That's where the MAC address came from, right? So that's where the usual address, and then the type is the IPv4, and the payload the actual IP, and the FCS. Destination MAC can be unicast, multicast, or broadcast. So source MAC address always unicast because that's the center. Type field indicates what kind of network layer protocol follows, like IPv4, IPv6, ARP, or VLAN, etc. Payload, usually an IP packet. Frame check sequence for error detection, so that the entire structure must fit within the maximum Ethernet frame size. So that's the usual bytes, right? But since the addition of this QTAG frame, which indicate virtual LAN, that usually indicated in type field, are now separated in PQ. Why frame size matters? The size of a basic Ethernet frame is 1518 bytes, but the more recent standard extended the size to 2000, means in the original Ethernet standard, the entire frame, destination plus source plus type plus payload plus FCS, could not exist 1518 bytes. So here's an example. Ethernet header, you have 14 bytes, payload 1500, FCS 4 bytes, DST 6 bytes, SRC 6 bytes, length 2, data payload up to 1500, CRC32. So here you have the type field identifies IPv4, IPv6, ARP, etc. So here we have 6 for DST. So this is actually the header, the DST and SRC that's included in the header. The payload could be part of the type length and the data, the actual data payload, and the FCS is the CR32. So the total is 6 plus 6 plus 2 plus 1500 plus 4 equals 1518 bytes. So this is the classic Ethernet frame used everywhere. Now that's Ethernet header, 18 bytes, payload 1500. Let's just stop here after because I think I'm gonna have a problem recording this. So this is the classic Ethernet frame used everywhere. Now Ethernet frame, here we have 18 bytes, payload 1500 bytes, FCS 4 bytes. So now these are the more updated ones, because for Ethernet header we don't just have 14 bytes, because we added the VLAN tag, the tag type, So the VLAN tab, the PQ format. So we have 6 plus 6 plus 4 plus 1500 plus 4 1520 bytes, usually rounded to 1522. So now we have VLAN ID or priority 802.1Q, 802.1P. So the priority is on, I mean, if it can only be applied if you're using like a virtual LAN instead of the old LAN, indicates presence of a VLAN. So that's 1522. You add 4 bytes for VLAN and priority tagging, because that VLAN actually needs to send a header including the VLAN ID. That's why it requires that additional 4 byte used for virtual LANs and quality of service. So if you want to define the quality of service within your app. Now Ethernet, so these are the more recent one, total up to 25 bytes. DST, the Ethernet header plus multiple tags up to 482 bytes. So now we have 6 plus 6 plus 2, the type, 6 plus for DSTS, or say 6 type 2 tag 4. Now we have 4 bytes for tag, and then another one for tag 2, 4 again, tag 3, 4 again. So we have 6 plus 6, 12 plus 12. We have 24 plus 1500 plus 4 up to 2000 bytes. So it allows stock VLANs, Q in Q. So the reason why it is up to 2000 is because it could allow stock VLAN to provide QoS, or priority quality of service. So it allows stock VLANs, Q and Q, provider bridging, and future extensibility. It is defined in IEEE 802.3 2008 as an envelope frame. So it started in 2008. So you can more so this 802.3 are the one of the part of the here that we discuss here, 802.3, the baseline Ethernet. So this is where the 2008 came from. So these are all the IEEE 802 LAN or MAN standards. It's still backward compatible with all Ethernet because it's more than that. So in the original IEEE 802.3 without the 2008 Ethernet specification, the payload or data field is up to 1500 byte. We have header of destination MAC, source MAC, which is all 6 bytes, type or length 2 bytes, and frame check sequence, which is 4 bytes. Plus 1500 equals 1518. So this is 1518 byte size is often called the maximum Ethernet frame size or MTU frame size, excluding the preamble and SFD. But with the more recent one, we now have the 2000. So as Ethernet evolved, new IEEE standard like 802.1Q and later 802.3 2008 introduced extra tags that could be added to a frame for VLAN identification, quality of service 802.1P, other protocol extensions. Each tag adds 4 bytes. So this VLAN identification, quality of service, and other protocol adds 4 bytes, and the standard allows for multiple tags, stock VLANs, or Q in Q. So to make room for these tags while still allowing the same 1500 byte payload, the IEEE extend maximal total frame size to 2000 byte, known as envelope frame. So there's the summary. Basic frame, the original internet frame 1518, QTAG frame 1522 only includes a single VLAN. So envelope frame allow multiple tags or extension up to 2000 bytes. So devices and switches must support the larger frame size if they process VLAN tags or other IEEE 802.1 features. So your devices and switches must support this to be able to configure or more configure the priority in your network. The payload MTU usually still remains 1500 bytes, but the total frame size, header plus tag plus FCS, can now legally be up to 2000 bytes. So in short, the original Ethernet frame could be at most 1518 bytes long, header plus payload plus ERC. Modern standard allow envelope frames that include extra protocol tags, increasing the total size of 2000 bytes, though the actual data payload 1500 bytes typically stays the same. So because of that extra protocol tags, VLAN, extra queue, etc., it could be 2000 bytes. So when they introduce additional fields like VLAN tag 0x800 adds 4 bytes, and 802.180 QNQ stock VLANs adds 8 bytes or more. Other encapsulation, MPLS, etc., the old 1518 byte limit wasn't enough anymore, so they extend the frame size up to 2000 bytes to allow these extra headers while still fitting the payload. So they extend this, the frame size up to 2000 bytes to allow these extra headers while still fitting the full payload. So how this fit with MAC addressing? The MAC addresses, destination and source field are still fixed as 6 byte each. That part doesn't change. What does change is the header section. It can have extra field. So this is usually the header that you are seeing for the packet that your IP module receive, that it decapsulate or demultiplex. It can have extra field like VLAN tags, and the payload size can slightly have larger than 1500 bytes. So the IP now could have slightly larger than that, as we will discuss in the next or future videos. That is actually more realistic today, a larger IP datagram. So the type field 0x800 for VLAN is what tells the receiver what to expect. If 0x800 IPv4 packet, if 0x86DD IPv6 packet, if 0x800 in the type field, it means it's VLAN tag frame. There's an extra 4 byte tag inserted after the type field if it's a VLAN. So this is why extended frame size matters. Without it, you'd have to reduce the payload to make space for tag, which isn't desirable. So why is this important for ARP and IPv6 multicast? So your quoted text mentioned ARP uses broadcast MAC address FFFFFFFFFF to find other host. So ARP uses broadcast to find the MAC address to find other hosts. ICMP uses multicast MAC address to discover neighbors. So for ARP, it used broadcast. For ICMP6, it used multicast to discover neighbors. So again, like the discovery in the previous video for DNS that we discussed. So both of these rely on link layer MAC address being at the beginning of the frame. So both of this protocol rely on the destination or MAC address being at the beginning of the frame. The extended frame size ensures there's room to carry this protocol plus any VLAN or other encapsulation without violating Ethernet limits. So summary table, destination MAC 6 bytes, extended frame still 6 bytes, source MAC is 6 byte, extended frame it's still 6 bytes, type or length still 2 bytes, extended frame still 2 bytes. However, this is the difference, the VLAN tag, so additional 4 bytes in 802.1q. QNQ/MPLS, which is optional, plus 4 bytes or more. Payload, IP, ARP, etc. For original frame, 100 bytes max. For extended frame, up to 2000 bytes now. FCS, original frame 4 bytes, extended frame still 4 bytes. So total frame 1518 and 2000 bytes. So in simple words, the MAC address part destination stays the same. But modern Ethernet allows bigger frames to fit extra link layer information like VLAN tags. So protocol like ARP and ICMPv6 still work even tag or encapsulated networks without shrinking the payload. So note, the original IEEE 802.3 specification treats the length or type field as length field instead of type field. So it treats that as a length instead of type. The field is thereby overloaded, uses for more than one purpose. The trick is to look at the value of the field Today, if the value in the field is greater than or equal to 1536, the field must contain a type value which is assigned by the standard to have value exceeding 1536. If the value of the field is 1500 or less, the field indicates the length. The full list of type is given by Ethernet types.